Hey everyone, welcome to this explainer. So today we're looking at something that honestly might sound a little dry at first glance, but it's actually one of the absolute most fascinating parts of global logistics. We're diving headfirst into a 188-page document known as MIL STD 20731E. Think of this not just as a dry set of rules, but as the ultimate survival guide. It's the exact science that prevents billion-dollar military equipment from failing before it ever even sees action. Picture this for a second. How in the world do you make sure a super delicate microchip or a highly sensitive optical sensor actually survived the journey straight into a war zone? We always obsess over the heavy armor on a tank or the aerodynamics of a fighter jet. But there's this entirely hidden science, a really extreme level of engineering required just to keep a simple cardboard box or a reusable plastic container totally intact during a chaotic worldwide deployment. Okay, let's dive into this. We're going to take a structured journey today, hitting 5 key areas: the stakes of military packaging, navigating the decision matrix, 5 methods of preservation, levels of packing protection, and finally, engineering the perfect container.
Right, let's kick things off with Section 1, the stakes of military packaging.
Now, you might be wondering, why go to such extreme lengths? Well, in the military supply chain, a single rusted part or a shattered component doesn't just mean a delayed delivery. It could mean a grounded jet, or worse, a compromised mission. Every single item packaged under the standard enters what's called the Defense Transportation System, or DTS. This isn't your local delivery truck. It's a massive, grueling, worldwide infrastructure supporting the Department of Defense in both peace and war. It involves aircraft, ships, railways, barges, and pipelines. It's a global journey where the environment itself is often the biggest enemy. We're talking incredibly high-stakes scenarios here. Think wartime deployment, keeping operational units sustained, moving heavy depot-level repairables, and even pulling off those crazy complex deliveries right out at sea. And it applies to literally everything, from a massive engine block down to an electrostatic discharge-sensitive item. You know, the kind of stuff that could be completely fried by a tiny invisible spark of static electricity. Moving right along, let's look at Section 2, navigating the decision matrix. So how exactly do logisticians figure out the specific armor a part needs? Well, they use a seriously complex flowchart directly from the standard. Before anyone even touches a piece of tape, logisticians literally decide the fate of every single item by running it through a massive checklist of variables. Is the item hazardous? Is it a consumable? Are the dimensions within specific limits? Does it need a specialized container? It's like a giant puzzle, highly rigorous and incredibly precise. Now, one of the absolute most critical factors in that whole matrix is the item's fragility factor. This is measured in G-forces, basically the maximum force acceleration an item can take without physically breaking. If an item has a fragility factor of less than 50 Gs, it's super delicate and needs specialized shock mitigation. But if it's 85 Gs or over, it's considered a bit tougher, what they call a common item. That one single metric lets them perfectly tailor the protection level. All right, that brings us to Section 3, 5 methods of preservation. This is where we get into how the military actively coats, seals, and defends its equipment against chemical and physical deterioration. They use this escalating ladder of defense. It kicks off with Method 10, which is just straightforward physical protection, your basic blocking and bracing. But as the environment gets harsher, the methods level up. Method 20 brings in preservative coatings. Method 30 seals it against liquid water. Method 40 steps up to block actual water vapor. And finally, Method 50, that's the top tier. Total water vapor-proof protection with active desiccant. Let's zoom in on Method 20 for a second, because the chemistry involved here is actually fascinating. To defeat corrosion, an item is meticulously cleaned and dried first. Then, it gets coated with contact preservatives, maybe by dipping it, flow coating, or even fogging it. Once it's fully coated, they wrap it snugly in grease-proof material. It essentially creates this physical and chemical barrier that stops rust and mold dead in their tracks before they can even take hold. But hey, if you want to see absolute mind-blowing precision, Method 50 is where it's at. They don't just toss a couple of moisture-absorbing packets into a box and call it a day. No way. They use actual algebraic formulas. Formula I and Formula 2 calculate the exact amount of activated desiccant needed based on the barrier area, the volume, and the pounds of dunnage inside. Plus, to prove it's actually working, they throw in a cobaltous chloride humidity indicator. It's a card with spots that physically change color to let you know, for sure, the internal climate is perfectly dry.
Okay, moving on to Section 4, levels of packing protection.
So,
The crucial point here is that once an item is perfectly preserved, it still needs an exterior shell. The military essentially splits this packing into two main levels. Level A is the heavy hitter, demanding the highest protection for the absolute harshest environments on Earth. We're talking direct exposure to extreme climate during deck loading or sitting out in open storage. That means heavy-duty, overseas-type wood boxes and reusable plastics. Level B, on the other hand, is for more moderate conditions, like if the item is tucked away in a containerized overseas shipment. You're always tailoring the shell to the expected threat.
And finally, let's wrap up with Section 5, engineering the perfect container. Because honestly, these boxes themselves are literal technological marvels. Think about the number 10. Under this standard, 10 is the minimum required trips for what they call a short-life multi-application container. These are usually made out of wood, plywood, or cushioned fiberboard. Just pause and think about that for a second. A box made of fiberboard, engineered to survive a minimum of 10 grueling trips through the military supply chain. But then we have the giant number 100. That's the minimum trip requirement for a long-life reusable container. These things are the absolute beasts of the logistics world. They're built from rugged plastic and packed with permanent internal shock mitigation systems, steel coils, springs, shear mounts, the whole shebang. Actually, the service life of these containers is expected to completely equal the service life of the actual military gear they're protecting. Crazy, right? And this brilliantly illustrates a really clever military system called the CDRS, the Container Design Retrieval System. See, designing a custom shock-absorbing shell from scratch is incredibly expensive. So before anyone is even allowed to engineer a brand new specialized container, they have to interrogate this centralized database. If an existing Department of Defense container can do the job, or maybe just be slightly tweaked to fit, they reuse the design. It's a massive money saver. So, what does this all mean? It really makes you step back and think, doesn't it? Imagine how our everyday commercial shipping would change if every single package dropped at your front door was engineered to survive 100 trips to the world's harshest environments. The massive gap between our everyday logistics and this invisible, extreme science of military packaging is just staggering. Thanks for hanging out with me for this explainer, and keep questioning how the world around you is put together.